So welcome back, everyone, to the weekly seminar series on fractional calculus. Today's speaker is Joel E. Restrepo. He is a Colombian mathematician and a researcher in the Department of Mathematics of Center for Research and Advanced Studies of the National Polytechnic Institute, CINVESTAV, Mexico City in Mexico. Previously, he was a postdoctoral researcher at different research centers in Belgium, Russia, and Kazakhstan. He has carried out mathematical research in a variety of topics connecting different areas of mathematics. His research links several techniques in complex analysis, operator theory, harmonic analysis, PDEs, etc. He has also participated in many international conferences, seminars, and other related events, and has been involved in the organization of several of these scientific projects as well. And today, he's going to speak to us about abstract wave-type equations with almost sectorial operators. Please, the floor is yours.
Thanks, Arran. First of all, hello everyone. Thanks to the organizer for this kind invitation. Well, I will speak about this abstract wave type equation. It's still under construction, the paper. So I will try to give some details, but I cannot give all because it's not released the paper. But we will see some important things like maybe the audience can understand. And also for the expert, I really sorry if I go very slow, but usually I normally try to do some motivation from the classical things. Also in the second part, we will give some classical results in Rn with this Caputo derivative and some Laplacian operator just to see how it's working, what I want to introduce, and so on. In the third part, I will speak about some type of operators which are called almost sectorial operators, and which is based the paper I am now working. And with these operators, we will recall some functional calculi that is regarding with these operators and that we can use to get the solution operator of some equation that we can consider. In the last part, we will speak about our equation I am considering, and here I will give you some details about the homogeneous part, but in general, I am now doing the semi-linear part and the linear part as well. So, well, let us begin with some classical things, just if for everyone wants to understand what is the idea, the general idea. So, I like to begin with the following heat equation in Rn. Here we have the one function which depends on the time of the space, x is in the space. Here we have the derivative, and here we have the Laplacian operator. So Rn is a very good space, and in this case, we can recall this transformation, which are this transform, like the Fourier transform and the inverse Fourier transform. Here I am not speaking about any functional space, but in general, with some good properties and some good decay of the function, we can just apply, for instance, in one, we can apply the Fourier transform and then get some ordinary differential equation in time and solve in this form how I am putting in this, like the Fourier inverse of the Fourier of the initial condition, and here we have the exponential in this order, okay? Here we have when we apply the Fourier transform of the Laplacian, we have the symbol and we recover the function. As I said, here Rn is very good. We have this transform and we can get explicitly the solution of this equation, which is local because depend of the derivative in the point. So that's the reason here we call normally this is a local operator, the derivative in time. So if we want to analyze this solution, here we have explicitly in Rn. So usually questions in this type of problems is about the well-posedness, regularity of the solution, how the solution in one space, I am not saying which space, it's just in general, in some space can be the solution can be bounded or can be related with the initial condition in another space. So I just put in red is how we can do this stuff in general settings. And also we can ask about the blow-up results, in which spaces they occur, and some other properties about the solution, and so on and so on. These are just classical questions. And again, this depends on the considered spaces and the nature of the space operator. In this case, if in this case we are taking the Laplacian, but if we have another operator, it depends also on how we can control or how we can work with such operator. So, as I said, Rn is a very good space, and we can get explicit the solution and get even optimal and sharp estimates. This is very well known, well studied, and there are a lot of words about this. So, thinking about the solution, how we did with the Fourier transform and the inverse Fourier transform is just one side of the one side on how we can get the solution. But what happens if we can represent the solution in some other way? So I said, people, let us suppose like we can solve this equation, the heat equation, in the following form. You have exponential in order minus t. Here we have the operator. Why the operator? Because if we derive, suppose everything is working like in the usual case, so delta is coming down, and then we have that this type of solution, we don't know at the beginning, we don't know how it's working, but this type of presentation of the solution is working somehow, right? It's a function which it depends on an operator. And this satisfies the equation if we know like the derivative of this exponential in order minus t delta. It's just the derivative is taking out the taking down, I mean the Laplacian and leaving the exponential normally. This is like a just thinking we can do that thing. So normally this is how we call a functional calculus for this operator. Which type of functions we can put to give a meaning of this type of expressions. So in this case, for instance, we say like this is an operator because it's taking functions in the space and going to the same space. Well, it depends on which space are you working. You can think about the L2 in some omega is an open set, or well, with some good boundaries. And then if we think about this operator E in order minus T delta, so the root of this operator is the exponential. And we say like this generate a zero semigroup if this means like it's a mapping where t is going from 0 plus infinity and is going to the bounded operators. This b in order x is means bounded operators. Usually it is taking complex Banach spaces, but you can just drop it this complex and get some generalization if you want. You have to be careful in this. So we say like it's a zero semigroup if in zero is the identity, and also it has this when you can when you have t plus r, you can just separate. This is this semigroup, and also when t is going to zero, or any x in the space, you have just this strong continuity in the norm of the Banach space. So in this case, for instance, this t is the exponential, right? We have like this operator is called generates as a zero semigroup and satisfies the condition, because when t is going to zero, it's just going the identity, and then you get the initial condition. So with this definition, we can see like somehow how it's working some operators. In general, all operators are no, for the heat equation, we have a good standard form to give for this representation of the operator, but in general, it's not true. These semigroup properties, for instance, we will see this in the case of the fractional time in the afterwards. We will see. So, for instance, trying to get these well-defined operators E in order minus T delta, there are some different characterization. It depends on where are you working and which condition you put over the semigroups. For instance, in this case, there is a very classical result about this characterization with Healy-Yoshida. If you have some generators of strongly continuous semigroups of linear operators on Banach spaces which are bounded by this exponential with some omega in R, so you just need to request to the operators, usually they are close, densely defined, and satisfies this condition we are looking here. So sometimes this is just for the resolvent when it's in the real axis. Of course, this is some good characterization, but it's just for resolvents on the real axis. So it's good in some sense, but still, if we have some if the resolvent is in some sector, so we don't have this characterization. So we have to think about some other characterization, how we can create these semigroups or this solution for these general equations over Banach spaces. So let us, for instance, take this general case when we have this heat equation. We can suppose like we are over a general Banach space, so well, we can have a locally compact group, etc. We have a Lie group. There are many cases, but I just put it like this to have a general idea how we can construct solution for this. So I put L is a good enough operator, and in general, in the interesting case, is always the unbounded case, because the bounded case is there are many things already developed, and I think hardly we can get something new. But for unbounded case, there are many things like to still we can develop, and there are many open questions and many things. So that's the interesting case. That's the reason I put unbounded and good enough. So when I said good enough, if we are thinking, for instance, in a Banach space, we are just thinking about close operator with some bounded in norm, something like that. Okay, so there are some, as I said, some functional calculus, which means which functions with this operator they have some meaning, or how we can get some bounded operators with these functions involved with the operator itself. So in this case, we have like again the exponential function, which is very good in infinity. So somehow we can have some functional calculus or homomorphic functional calculus, which I will explain in the other afterwards I will explain how we can construct these operators, which are called solution operators, and which are the way how we can think in general spaces, because here we don't have in Fourier transform or more explicit things. So that's the reason the functional calculus must be developed, and it depends on which class or type of function you can involve with this operator. again, with these operators, we can ask about existence, uniqueness, asymptotic behavior, norm estimates, properties about the solution of this differential equation or integral equation. So for instance, just think about the particular case if you want to get the LP-LQ norm estimates of the solution. So usually what you want is if you have a data in LP, you want to see how is related with the solution in LQ, related with the norm. So what you want is something like the solution of this heat equation, which is E in order minus T of the operator, evaluated in the initial condition in LQ. You want to get the initial data in the where is the base space, which is LP here, and somehow you want to estimate this propagator. You see here we have this propagator or operator, whatever you want to call, in some good space, certain space I put G, where you can handle and you can calculate such a things. So this type of problems, this type of questions are related with the spectral invariant multipliers, which is there are a lot in the literature, and spectral ones a lot of things. So this is just an idea of how we can think about these problems, how they are, why these are very interesting objects to study, and so on. So something interesting to say is that many authors they assumed operators densely defined, but people sometimes don't understand this situation. So here I want to just show why this is important and why densely defined operators usually are related with unbounded type operators. Let us check this, for instance, this example. Here we have an operator where the domain is in a separable Hilbert space and his positive linear operator densely defined. Here positive we mean like the spectrum is 0 plus infinity, and in this case the assumption of densely defined operator allows us to think about operators of a bounded type. Why? Then we will see why. If we define this operator over the whole space, for instance, over the Hilbert space, assuming that this is a complex Hilbert space and which is positive as we are taking here, so there is this theorem of Hellinger-Topliss theorem, which says like this operator is bounded. So what we are looking here is that taking operators over the whole space sometimes is just arriving us to the bounded case, which is not the interesting case. So that's the reason usually is defined densely defined. Just this is a good observation for some people. Maybe they want to learn about this and why they want to understand why densely defined and not over the whole space. So let us go now to the well, I like to say no local in heat type equation because people, well, some journals I can say some journals they don't like to listen the word fractional, but no local also is accepted in the community, so I prefer to use like that. Here we have the Caputo derivative, which is this integral, the 0 t minus s in order minus beta. We have a singularity of order beta in 0, 1, and the derivative of the function inside with respect to s. So it's not local because we know that it depends on what happened in 0 t. And here again we have the Laplacian. I want to illustrate what is the difference in how we can go to the more general case. So we will begin with this case in our end. Again, here the solution, we can get this solution by taking the Fourier transform and after that solving the ordinary differential equation in time, well, in time, see, yeah. And after that, applying the inverse Fourier transform. We have a very good how to say, explicit form of the solution. We can get sharp estimates. There are some good papers available in this in this type of equation. Like they already know what is the best constant for some problems, sharp constant, and so on. Here we have like the solution is related with the Mehta-Leffer function. I hope many people know about this. And again, if we want to study the general equation, if you see here, I can put this Mehta-Leffer function which depends of the operator inside. Why? Because I want to come back here a little bit. When just suppose beta, we can put beta equal 1. In the last representation, we have the heat equation, and here we have an exponential function. And this was the root of our solution when we get to the general term. So usually, when we are analyzing this case with a general operator, we can then somehow think like this is the root of this function, of this operator. So in this case, we have to ask about how is this operator, when we can write this operator, if it is bounded like is it strongly continuous, if it is semi-group, and as we were looking before, there are some characterization for this or not. So all these questions, there are different forms and operators people use usually for this. I will like to write the following one when beta is in 0, 2. Here they consider the heat equation and also the wave equation. I mean the fractional wave equation and the fractional heat equation in a general band space. I put here Prash. There is a good book on the evolutionary integral equation and Vaslekova that have a very good general thesis, which is a very good standard, for many people just to get into band spaces, equation on band spaces with fractional operators. So in this case, with some good properties over the operator, they usually they use some positive operator with some conditions. I don't want to remember this now, but what I wanted to say is they have some good condition over the operator. They can write these operators in a very explicit form, which depends of the resolvent operator. Here we can see in the other side of the representation, where here H, capital H, is in the resolvent set of the operator, of minus the operator. So why this? Well, some people they think how we can get this representation. Well, these representations are very close related with the representation we have for the case of when we have the Mehta-Leffer function in the complex plane. So here I put just the representation in the complex plane just to see how it's related somehow. I'm not saying it's the same, but somehow it's related. And there are many things it can be related to get this type of representation in a general band space. In this case, what we can say about the solution operator, for instance, for this Mehta-Leffer function, we can say these operators, which are bounded for any t more equal to 0, are called solution operator of this fractional heat equation if this operator is strongly continuous for any t more equal to 0. In 0 is the identity. And something interesting is we don't have the semigroup, low, but we have somehow like this operator can commute with the operator itself, with the L of considering the equation. This is very important because sometimes when we want to get some good properties, for instance, of semi-linear or linear equations, we need this property, and sometimes it's not working like this. So it's not working. I mean, you cannot always change both operator, but in this case, it is working when the initial data is in the domain of the operator. And here we have, of course, like this is the solution operator, it satisfies the equation with the considered initial data. So there are some different, there are no semi-group law, but still we can work with this second condition in a good way. Well, something like I would like to remind now is about the fractional heat propagator on some Banach spaces. Why? Is because this propagator can be related with the classical heat propagator. So many conditions which we need for this for analyzing this solution in the fractional case, it depends of the classical case. This is very interesting. So here, just suppose we are in a general complex Banach space and we have a well, I like to say the Gervasian Caputo fractional derivative, but well, many people just call Caputo fractional derivative, the usual one, alpha in C1, and we have here a closed linear operator, which is sectorial one. So here we change a little bit. I want to explain this. Sectorial one means like the spectrum of the operator is in a sector of the complex plane. And moreover, the resolvent operator of this one satisfying like is less or equal 1 divided by modulus of the spectral value we are taking out of this sector without where we are taking just values out of the sector where is the spectrum of this operator. So for this type of operator and other ones, we know very well how is the solution and we know how to express. There are different types of solution how we can express. Why I am mentioning here the sectorial ones is because over the 80 years around this, sectorial operators are very well studied, very well known, and then people now, well, in the last 20 years, people were studying these operators as well with fractional time operators. So in this case, as I was saying, there are different types of presenting the solution operator. And in our case, in this case, I want just to present this one, which the operator depends, see the right hand side, depends of the heat propagator. Because we have E in order minus ST in order alpha, the operator. So this means like the propagator of the fractional of this fractional time fractional heat equation depends on the classical heat equation. And this function is a right type function which has very good properties. So when we are analyzing this case, many things are coming from the heat case. So it's, I can say, easier than the weight type, because the weight type, we don't have such a representation. In this case, this representation is revealing a lot of good things, because we can get even sharp estimates and so on, because we know many things. I mean, at least for the heat propagator, a lot of things are known. So a lot of people is working with this estimates, I mean, with this representation to get very good estimates and to get the results in this type of works with the heat equation, fractional heat equation, sorry. So just to get a difference, this case, with respect to the weight type. So in this third part, I want first to introduce some notations, and I will speak now about which problem I was attacking, and I needed to introduce all this stuff because you will understand easier what I will say now. So now we will assume like we have a complex Banach space, and this is the norm there. Usually an operator for ice, which means a linear map, which it has a domain inside of the Banach space. The domain is a linear subspace of X. Sigma A is the spectrum, and here we have the rank of the operator as well. And well, sometimes here we denote this Lx, the space of all bounded linear operators on X, okay? And from now, if we have a mu in 0p, we will just denote for this mu zero, S mu zero, this open sector, which are all complex numbers, which arguments are less than mu, okay, without the zero. And its closure, S mu, is just all the sector with the zero and the lines of the rays here. So we will introduce somehow the operators I am now working is this class of operators, which are closed linear operators, such that the spectrum is in a sector of the complex plane and such that the resolvent satisfies this condition. As you can see here, gamma is in minus 1, 0 in this interval. So this type of studies began a long time ago, in the 70s, I can say. With this, I put this for references, but there are some other ones which are just semi-groups, they said with singularities or with growth or some growths in the resolvent here in this case. Here I just put some of them where you can find more details about which operator satisfies this type of things, okay? So usually when gamma is 1, this is the well-studied case, which is the sectorial operators. So a linear operator, it will be called an almost sectorial operator if it's in this class, okay? If the spectrum is in some sector and the resolvent satisfies this condition. Now we will give some examples of this. Well, here I am just showing some picture on how the spectrum is in some sector, and the other one is where the resolvent satisfies such a condition, okay? Here is just to have some picture on how it's working. And well, before giving some one example, I would like to give some properties of these almost sectorial operators. Is like for instance, the first one is 0 is in the spectrum of the operator, and also there are injected operators. And there are many things you can check, but there is a good paper of Periago and Straub where they construct the functional calculus for these almost sectorial operators and give some applications. So you can check there. There are some properties. Well, they prove these properties there. And what is also important in this class of operators I am working now is that they have the possibility to have dense domains, which usually, in many words, we are just assuming, and here they also don't have no dense even range. So this is a different panorama with the classical results even, because sometimes we need this condition. Of course, there are some people they work with almost sectorial operators with had dense domains. Now, in my case, I am not assuming such a thing. Okay, just to get more generality. So I will like here to just give some examples of where are arising these operators, and we have like there are a lot of sectorial operators which usually they appear in Lebesgue spaces and continuous functions. Sectorial operators, okay? But when we are going to more regular spaces, like Hölder continuous functions, they are not sectorial. Here, in this case, they are almost sectorial. So I put here some references where you can check such a thing. I put Leonardi, she has a lot of examples of this. I put Walsh here. There is a good example here also. And Periago and Stroud, they have a lot of things about these almost sectorial operators, okay? Well, what is the difference and so on. So, okay, as I said, I want to show here how I constructed the solution operators of the wave equation. So, in this case, the authors, Periago and Stroud, they use some holomorphic functional calculus. So they are getting some class of holomorphic functions, and the other ones like are bounded by 1 divided by 1 plus zeta. And this is some holomorphic functions which are bounded. I don't want to give a lot of details about this, but in general, what we want is like the modulus of the function must be bounded or in some sector of the complex plane, or modulus of the function is less or equal 1 divided by 1 plus zeta, and zeta is different to minus 1. Something like that we will use, and I will say in our, as we are using Mehta-Leffer function, this is enough for us. So here, of course, there are some, I put all the details just for people if they want to check later. But in general, there are some different classes of holomorphic functions, and just you need boundedness of this holomorphic function in a good way in the sector, just to get some good representation for the function in these classes. So the first results I want to show here is the for this class is here. Just think about a function which is modulus of this f zeta is bounded or is less or equal 1 divided by 1 plus zeta. So in this case, we can get this integral representing this integral is absolutely convergent, and it defines a bounded linear operator. Also, something important is like it doesn't depend of the theta you get you put in this. It doesn't depend of the choice of this. So what we are saying here is like there are some class of functions we can represent like this somehow, just to get some idea, like a Cauchy integral, something like that, just to people to get some analogs on this. And which is important is it's absolutely convergent, and also it defines a bounded linear operator. Okay, the proof of this is based on the taking a good region in the complex plane and applying, of course, the the classical result we know in complex analysis. Why this is important is because we can get several properties with these operators, and we can say something like, for instance, if you have two functions in the class, the product is there also, and moreover, you can get like the product is both integral FA GA here. This is very interesting because in the future, when we need to prove like this is the solution, some of these conditions are very important to and very easy to handle it to get to apply for getting like this is the solution, whatever you want, my solution, weak solution, or classical solution. Okay, So here there are some characterization for the product operator, and also it can be just I wanted to show like there are some good properties we can use with this functional calculus. So one example, like the typical sample for this class of functions is to get here we have t in some region of the complex plane. This restriction are needed to get like at least the function is very good and bounded in this region. So don't well right now I don't want to explain a lot for this restriction, but they are necessary. I can say like that. And then here we have like this function exponential in order minus t zeta in order alpha, and the operator in our class almost sectorial operator gamma is -1 0, and then using the last theorem like I said about the functional calculus, we can prove like this function is in the class, and then we can represent such operator, this exponential in order minus t a in order alpha, like this integral. And moreover, is convergent and is a bounded linear operator in our Banach space. So in particular, it holds for alpha in 0, 1, and this expression we can also denote by this e minus t e in order alpha. So this is like the fractional heat propagator in a general sense, like we can think how is this operator. Of course, we have to be careful because this is not the same strongly continuous semigroup. We have to be careful because the norm of this operator is satisfies at different bounds. We will see. For instance, in this case, we have like of course, it's a semigroup, satisfies a semigroup property, but the norm of this operator is less or equal than t minus this quantity. This means like there is a strong continuity in t equals 0. So this is the great difference with some other propagators in some other cases, is that for almost sectorial operator, usually there is a discontinuity in t equals 0. And there are some other properties, like when we multiply by an operator in order beta, so we get some estimates, and also we can work with that. And which is interesting with this representation, as we know in a good region is analytic in T, and moreover the derivative is just what we can expect, what everyone maybe must know. So in the last part now I will say some, well, it seems a lot of just in some 10 minutes I will reveal like what I was thinking, what I was doing, and how. So here what we are considering is the Caputo derivative, but with the ordering 1, 2, just to try to consider the weight type equation. And here we have an operator which is an almost sectorial operator, and we have to score some bounds on the sector which are necessary, and which it depends on the bounds we can get for the Mehta-Leffer function. In principle, the data, it can be taken over the whole space, but there are some details. Depends on the solution you want to get. You need to take care of this data. So these words are just some continuation of the first word of the case when alpha was in 0, 1. It was done in this paper, abstract fraction and Cauchy problems with almost sectorial operators, published in JDE in 2012. Just 12 years ago, well, 13 years ago. And well, I just realized I was doing this work from last year, and I realized like in this year somebody published something about the wave equation but still he didn't the linear and semilinear case, but it was published in this. Some Chilean colleagues, they already published something about this equation and how is the solution, how are the propagators, and so on. Well, still we have some different methods to do some things, so it's a different approach. You can check this paper also is good to see how they did the things, what they analyzed. They analyze also different spaces, like a holder spaces and some other things. So what I was interested to do, it was usually people, they like to analyze my solution, but in my opinion, the most interesting case is the classical solution of this wave equation, which is a function which is continuous on the closed interval you will consider over the Banach space, and the Caputo derivative of the function must be also continuous, but over the, here we are taking out the zero, you see? It's continuous, but without taking the first point. The function must be in the domain, and of course, this solution satisfies the problem. So I am working now on this, getting a classical solution, and the solution is connected with the following operator, which are related with the Mehta-Leffer functions. And here I put it. I just put it, and I didn't say how I get, but I will just in the next slide, I will reveal how we can get this type of thing. So maybe you just imagine using the functional calculus. So here we have those two operators, which are close related because the second one is just the one convolution with the first one. So here I said this, we have this equality here, T of this Mehta-Leffer function with the parameter alpha 2 is equal to this convolution. Well, I put set in all C, and so we can rewrite. Well, here we have to be careful. I am not sure if it's in the whole zeta, but yeah, we have to be careful here. Still, using this where this equality is true, we can rewrite then this operator. Okay. So what I was thinking is like, okay, the solution was related with these operators, but I think we can get more general class of operators, and then taking a good sector of the complex plane where this has a good decay, we can get like this function is in our class, like it was defined by Periago and Strauss, and get like this operator with delta any real number and alpha less than 2, we can get this representation for such operator, and it's linear and it's bounded. How we can, well, and also we can also get like this operator is strongly continuous for any t0 more than 0. In 0 there are some problems again because we have the resolvent of this operator, it has some singularity. When we want to get some boundaries of this integral, we have some problem. That's the reason we need t0 more than 0. And also, in this case, the norm of these operators, it has an order t minus alpha 1 plus gamma. So we have also a strong singularity in 0. The second part, well, of this theorem is like we have this, there are some, is say infinity differentiable, I put like this, and we have even such a equality, and also it defines a bounded linear operator. This is a more general form of some operators here, and we can just bound these things, and again it has some singularities when in t equals 0. Well, here again I repeat like this is the Mehta-Leffer function, just to remember. But the most important for doing all this, this stuff and these operators is with respect to this condition we have. So over the Mehta-Leffer function, which everyone maybe must know or have used, that is bounded by 1 divided by 1 plus zeta, but the interesting thing is where is this element of zeta? Here we need like this zeta, it must be more than mu and less or equal p. And in this case, with alpha is more than 1 in our case, so we have like this is in the second part of the complex payment. I mean 1, 2, 3, 4. Can divide and see like I can show here the region which zetas we can use in our representation to get such a inequality. So we have to be careful with this when we want to use the functional calculi. Okay, this is very important. That's the reason I put where is theta you can take in which zone of the complex plane. So after that, as a consequence, we have like for these operators, when we have a good sector, a mu in the good sector, here we need this sector. I think this was the optimal one. We cannot get better, I think so. Yeah, I couldn't get better. Maybe I must say see this. And then the operators, like they are related with the solution of the wave equation. These operators are continuous differentiable in say infinity, continuous differentiable in 0 plus infinity. They have singularities in 0. They are bounded linear operators, and also we have this norm estimates for them. When we are working with the linear and semilinear equations, something very important, like we need to ask, is what happened with the operator when we apply the propagator when we apply the operator, if how we can get a good representation or not. So what we can see in this case, the best thing we have is like in this case, this operator zeta, and we have this Mehta lever with alpha minus n. For n equal to 0, any natural number, we can get like this expression. Not always you can get such expression because we need some good decay. So in this case, we can give, this is the best you can do it in this case. Well, this is a partial answer, but I couldn't get a better thing in this case. Okay. And here we have some decay, good decay, the best we can do with this representation and what we have. This is, of course, some properties with some propagators that we need to use to prove the classical solution for the linear and semilinear case, not in the homogeneous type. So by the last theorem, we can see like this operator belongs to the domain of A. And also it's clear, like you remember, like when we have two functions and one of these is bounded, so you can separate the operator. That is very important property. And then we have this second remark. Another important thing is like sometimes the representation we give here is depends on the Mehta lever function, but for the Mehta lever function it's difficult to find some sharp estimation. That's why we need to rewrite this propagator in another form, and then some things for this can be revealed by, first of all, rewriting some taking some good Hankel path. Here we have a good Hankel path, and then taking some condition over the. This is like I put a counterpart of the resolvent operator because here we have plus and we don't have minus. And then what we are saying is like we have a similar condition as we have in the resolvent case, but in this Hankel path. Okay. Here lambda is in this Hankel path. This is some conditions we need to just to apply for getting the new representation, which is this one. And then here, what we are rewriting the operator we were getting by the functional calculus, but again with the Mehta function inside, sometimes we cannot give good estimates, and therefore we need to rewrite this solution in this form. And moreover, with this solution in this form, we can see like this is strongly continuous if the data or the element we are taking is in the domain of A. This is a very important theorem we use sometimes. And something very important also for people in general when you want to get uniqueness of the solution in an easy form is the Laplace transform of this operator. So what you can get is the Laplace transform of the operator in the first case, I mean in the Mehta function of alpha. We need here one extra condition, which is, well, we need for the convergence of some of the Laplace transform. So this is unavoidable, and this is the best we can do in this case. If we want to use these such a things that I put in red, there are some other properties with derivative of this propagator, the first propagator we can use in a good way, and taking some extra conditions, we get some estimates and we get some limit is going to zero, which is helping us for proving like the solution is a classical solution. So I just wanted to show in general some things maybe like you wanted to know. And then one of the main results like I have gotten is that the solution, when the data is in the domain of A, then the classical solution is given for these two operators. And of course, what we need to get is like when this data is in X, what we get. And there are some aspects like we can say, for instance, W0, the first initial data is in X, and the second one is 0, omega 1. So we are losing the continuity of the classical solution at t equals 0. So we can just guarantee this thing. So taking some data in the more general space, you are losing something, nothing like this condition. Sometimes we are putting in the result, but it's forgetting sufficient condition to guarantee the continuity of the propagator at t equals 0. So if we drop this condition, we don't know what happened. And this is an open question, and I didn't see any result for the hit case as well. It was putting this condition as well. And here you can just check this theorem 4.1 from this published paper of 2012. Also, if we put omega 1 equal to 0, there are an additional condition which is not necessary, and this is it will be appearing in the paper. Like if you drop this condition, what happened? Because everything is very confused, but in the end, you must be careful which condition are you using in some cases, okay? And of course, there are, well, I don't want to give this result because it's just a consequences of the lab results, which means like you can also consider the power of the operator and you can get some extra condition, but in general it's the same idea. And there are some just extra things you can check later, but it's almost the same. It's just some result which follows from the main one. And again, as I said at the beginning, I just wanted to speak about the homogeneous case, but in this case, I am also considering the semi-linear and the linear case, okay? I am almost finishing this stuff and just focusing on a classical solution. I know like many people, they like to do mild solution and later ask about which condition you need to the mild solution to be classical, but it's very standard for me. I don't want to do this. Maybe somebody will do, but I will just focus on the classical solution. And I hope I can release soon the paper and maybe share with all of you. Thank you very much.
Thank you very much, Joel, for the nice talk. Do we have any questions, comments? You can raise your hand or you can just unmute and speak directly. We don't have so many people in the meeting.
Could I say something because I cannot hand my hand. It is very beautiful talk. I am really impressed, and here I will make some recommendation of my paper because your paper is very mathematical, and in this year I made something similar, but I'm physicist, so it is not exactly the same. But instead of Kaput-Derbashian derivative, I used some memory functions. And it would be very nice if we can apply it, or you can apply your method to the memory functions. Because memory functions, I will send you this paper. But memory functions, we assume that it is the stealthiest functions of real line. So you know some rules of them.
Yes.
The Kaput-Derbashian is example of these memory functions.
You mean you are doing with kernels? Of course, yeah.
Yes, with kernel. Yes. I'm doing with the kernel. I'm not. I belong to this group of the people who are not using the fractional calculus, just non-local. And this locality is described by the memory kernel. Okay.
By the way, and you are doing with almost sectorial operators, right?
Exactly.
Oh my goodness. Okay. No, I have to release this soon. Yes. I understand. No, it will be this will be a particular case, by the way. If
not particular case, what you present on
mine, it will be particular.
Yes, it will be really something great to find the mathematical background by using the memory functions, because we are playing with stealthiest function on real line.
Yeah, I understand. You mean, well, I was doing this, trying to do this faster because I know the second step is to do the memory function. I am sure of that, yes. But if you are doing now one step back.
Yeah, but it is not formal mathematically, it's just the imagination of physicists.
Well, it will be great to have such a paper and to see how well, because you are giving the application, right? Well,
yeah, I will send you the paper. Your talk was really beautiful. I like it.
Thank you.
Very much.
Yeah, I know, because many people, they ask for application, and I always say, well, I don't like to go to this side because it's very difficult. But they don't like my answer. But I said, well, mathematical part is also very hard, so to go for application is very. But it will be interesting. I will be grateful if you can share this with me.
Because I found your email. It's sorry, here where I have your email on the paper.
If you want, I can send an email to both of you just to put you in contact
with each other. Yes, please send me
really.
email. Yeah, and I will write because I like it.
Thank you. No, really, I will appreciate your paper. Really, thank you.
Yeah. Thank you. So I mute myself.
Thank you, Katarzyna, for the nice comments. Any other questions?
If I may propose as an extension of this study, so I would propose to have nonlinear terms in the construction of the PDE itself, and this finds application in turbulence, for instance, there is a work called fractional Navier strokes. So they have fractional. So in the work by Jack Lyons, they have fractional in space. It's basically a Navier-Stokes equation with the fractional term in space. But there is another version of fractional Navier-Stokes, which is my version, where I have fractional in time, fractional in space, fractional transport in space as well. So there was a talk by Daniel who did the analysis for the fractional Navier-Stokes, the Jack Lyons version of it. And probably that might be an interesting thing for you to look into or extend the study, because that's just an operator in space, but then you can include in time as well and look into what kind of analysis.
You are right. Yeah, this is, I did a paper on it when the operator depends of time as well. There are some people, they are also doing this, and they are doing, well, in my opinion, they are doing very fast because they think like everything is the same, but you must be careful. They are just doing some similar, I saw a few papers, but yeah, we have to be careful how we are working with such operators because it depends the time and also the space, right? The operator. Yeah, I am also trying to consider such a case, and it will be also good if you can share some ideas of this.
Yeah, so I shared two links in the chat box. I mean, these are the talks that we organized last year. So I'm more of a, so my work is more about mathematical modeling. So I cannot talk about the questions that you are actually talking about, but I can give you a brief idea of like where it finds an application. So apparently turbulence is a non-local process. So to model turbulence, one can talk about having a non-local operator, which is a fractional operator. So that was the idea of Jack Lyons as well, but he fractionalized the Laplacian in the Navier-Stokes equation, and that's one of the earliest known work about it. But apparently that's more like a model to me, and I had a similar version of it to look into time average fields, which I call fractional Navier-Stokes. So these equations more or less are look identical, but one is a stochastic field and the other is a mean field. But both of these are more like a model. But however, so this was a little unhappy about it. So when you derive it from first principles, like you have the Newton's second law embedded in it, and then you start from it deriving it. What I found that I have a fractional in time, and the argument of fractional in time was a transport term, which is also fractional. That equals to a fractional in Laplacian and a pressure as well. So that equation turned out to be very complicated. I still don't have a numerical method to actually look into how to solve such equations. I'm working on it, but nonetheless, some mathematical results on that part would be appreciated. Of course, Navier-Stokes itself is a millennial problem, but one can look into simplified versions of it, like okay, one time, one space, and then keep adding it subsequently. So that would complement greatly my work as well. I've shared some links,
Thanks.
and and I can share you my previous paper as well, which might be an interesting thing for you uh, uh, to look into where this finds application.
Yeah. I saw somewhere on some weak version of these Navier-Stokes equations, and some people even use fractional and publish in a very good journals, and good papers and good approximations for this. At least not the millennium problem, but something related. That's good.
Yeah, I mean, eventually we go there. So, but at least we can start thinking about it, like adding one fraction in time space and then going around. So I've shared you the links. Probably Aaron, you can collect these links as well, and when you write to Joel and this, you can include these links too.
Yeah, sure. I'll just make a copy of these three links now.
Yeah.
Thank you.
Yeah. So, but these are my papers, or my work is more on the application side.
Sure. It will be good to see.
Thank you.
Okay, thank you, Pavan. Any further comments, questions?
Yeah, I have some questions. Hi, everyone.
Hello,
Nice seeing you.
Carlos.
Hope you are doing well. I missed some part of the presentation. Before maybe you mentioned at some point that the Caputo derivative is not was not continuous on the closed interval 0t. But half open interval 0t, do you have an example of a
Which one? This
problem
one?
where you have these properties? Yeah, I think somewhere d alpha t of u.
The classical solution, you mean?
Yes.
Well, I
It was
mentioned,
before.
I
Yeah,
mentioned here.
here. Yes.
Well, today I was speaking with Arran about this because, people believes like all functions, this Caputo derivative of all functions are always continuous in the closed interval, but this is not always
Yes.
happen. There are some functions like they have singularities like x in order minus alpha and alpha in 0, 1. If you derivate this, I think that was the sample, right, Arran?
Yeah, but at the same time, if a function is continuous only on the open interval, then it's... no, sorry, you assume W is continuous on the closed interval. So then the Caputo derivative at least will exist if you have a differentiability condition. Because I was going to say, if it's continuous only on the open interval, that's not enough for the fractional operators to even be defined.
Exactly. That's what I wanted to say to Karel.
That's why they use these Dymowski spaces, because they control the singularity at the initial value to be such that it must be integrable.
So, for instance, you have a God function. Well, but you want an example of this, right?
Yeah,
Well,
I was wondering.
A function. Well, of course, if we take x in order minus alpha in this case, no, because we have it's not continuous in the close, right? Not sure here. Not sure, but I will think about this.
Maybe you can think about it, and
it's a very good question
send me.
Because this is the classic. Well, I don't remember in the paper of 2012 they give an example. I'm not sure, but usually I like to think about this. But in this time, no, well.
No problem. And maybe some other question. You have alpha is constant. Can you also consider alpha, for example, time dependent?
When what?
So the alpha, the order of Caputo derivative is a constant between 0 and 1. Can you consider time dependent alpha?
But in 0, 1 is done. In 0, 1, this paper is already published in this paper. I said this. I put in the slides, see, abstract fractional Cauchy problems with almost sectorial operators. They did.
No, but he's asking about variable order, like if alpha depends on...
Can you...
Again.
Yeah, if alpha depends on t, also... So if
alpha depends on t? No, I don't think... No. This is... I'm not sure even how it can be done. Not sure. No, I didn't think. When you want to prove this classical solution, it's not easy to handle it. Such operators in this generality. And even I don't know how it can be represent the solution. Because even in the classical case, in the real case, you don't have such a representation, right? You have approximations. Karel, right? Because you work with
that. It's even a classical case, it's not completely solved. So
exactly. So no, of course here I didn't see any paper on this. I mean on Banach spaces, didn't see.
Okay. Thank you, Joel.
No, thank you, Karel. And I will think about your question. It's a very good question, by the way. And I don't have an example. Well, it's strange. Yeah.
Okay, thank you, Karel. Any other questions, comments? If not, then I will stop the recording, and thanks again to the speaker.